Good morning, good afternoon, and good evening, everyone from all around the globe. My name is Eric Mail, and I'll be helping moderate today's webinar, GPU Programming in Julia. In this webinar, we will cover the different Julia packages and programming models for working with GPUs, how to install and use them, and what tools are available to efficiently develop a GPU application or accelerate an existing code base. In addition, we'll be highlighting NVIDIA's hardware using CUDA software. We'd like to have this an interactive session today, so please write your questions in the chat, and we'll either address them on the fly or address each question individually following the demonstration. Please also, if you could mute your lines, that'd be greatly appreciated. With that said, I'd like to introduce you to today's presenter, Dr. Tim Besard. Tim is a software engineer at Julia Computing working on compiler technology and is responsible for the CUDA GPU backend of the Julia programming language. Dr. Besard received his Ph.D. in computer science engineering from the University of Ghent in Belgium for research abstractions to program hardware accelerators and high-level programming languages like Julia. Please welcome Dr. Tim Besard.
Thank you, Eric, for the introduction. So welcome everybody to this webinar. Today we'll be talking about how you work with GPUs from the high-level Julia programming language. This is the second iteration of this webinar. For people who have joined the previous one about a year ago, there's some differences. Most of the content is the same. However, there's some additional information on profiling, tools, and how to debug code. And of course, everything has been updated to match new and changed APIs in Julia and CUDA. So I'll start with a brief introduction on the Julia programming language. I'm going to assume that you're somewhat familiar with the language, but I will be explaining why it is an interesting language to use for GPU programming. I'll then be explaining the different programming styles, either array programming or kernel programming. And in between, I'll detail how you measure performance of GPU applications and how you profile your code. And finally, I'll be discussing some advanced topics. And as you can see here, quite some topics will be specific to NVIDIA CUDA and the CUDA.jl package we have developed for Julia. However, many of these concepts will be portable to other backends. So even if you're interested in using, say, the Intel or the AMD backend, this webinar will be interesting to you. So first of all, the Julia programming language. As we all know, or as I hope you do, Julia is a very interesting language for CPU programming. It has a proven track record of nice, powerful, and high-level features. For example, we have dynamic type, we have the versatile type system, you can do some powerful meta programming, and all of that still is there with some great performance on the CPU, at least. So it's a high-level language, but we don't sacrifice performance. We've been working on making this available on the GPU as well. There's a lot of compiler technology that actually has went into this to make this a possibility, but that's out of scope for this webinar, for this presentation. Needless to say, if you look at the chart on the right, we're comparing some benchmarks that have been written for the Rodinia benchmark suite, and this is comparing the performance of the benchmarks ported to Julia versus their reference performance in CUDA-C. And as you can see, again, we can use a high-level Julia language for GPU programming without sacrificing performance. And as a result, that solves the so-called two-language problem, which means that instead of having to use separate languages to work on, for example, the performance-sensitive parts of your application, you can use a single language, Julia here, to work both on the application or in the specific cases to GPU programming in Julia, the array programming model and the kernel programming model. So let me illustrate. We have a couple of applications in Julia that are GPU capable. For example, we have the climate suite of climatology applications. We have the differential equation suites of, again, differential equation solvers. We have some quantum algorithm design framework. And of course, we have a machine learning framework called flux.gl. And in the case of Flux, if you want to use a GPU, you just instantiate your model, you instantiate your data, and you pipe it to the GPU by using this flux-specific GPU function. But in the other applications I'm mentioning here, it's a similar easy way of just flipping a toggle or using a single function to have stuff run on the GPU. And much of that is made possible by the fact that Julia has these generic array abstractions. So you can just typically use any GPU package you want, and then if you instantiate some data, you can typically create a GPU array from that. And after that, you can perform generic operations. For example, here I'm broadcasting the sign function and then taking the sum of the array, which looks fully generic. There's nothing GPU specific about that. But because of how Julia has been designed and the fact that we can program GPUs with array types, we get automatic GPU execution. We have a couple of packages that implement such an array type for GPUs. We have accelerator.gl, which you can use to program TPUs. We have recently gained oneAPI.gl, which you can use to work with Intel GPUs. We have AMD GPU.gl, which, as the name tells you, you can use to work with AMD GPUs. And of course, we have CUDA.gl, which you can use for programming NVIDIA GPUs. I'm going to focus on CUDA.gl because it's the package I've been working on for most of my time, but it's also the most mature GPU programming package we have. It also features this powerful kernel level programming model where if in the case your array code isn't flexible enough or you need to do something very high performance, you can still drop down to the kernel programming level. That's not available for all packages, but it is available for CUDA.gl, AMD GPU.gl, and oneAPI.gl. As you can see here, this code strongly resembles what people may be used to using in CUDA. Nonetheless, much of the concept I will be explaining about kernel programming and also applies to these other three packages. And that's because recently we've been building more and more functionality on top of this generic base of GPU functionality. We nowadays have GPU arrays.gl, which contains GPU vendor agnostic definitions of many of these array operations, sorry. And GPU compiler.gl, which is a common base for GPU compiler functionality. And as a result, much of the things I'll be talking about during this presentation will also apply to AMD GPU.gl and oneAPI.gl. Of course, something that's fairly specific is the installation of these packages. And in the case of CUDA.gl, it's fairly trivial, nowadays at least. It only requires you to have a functional NVIDIA driver. Once you have that, you can just start by opening up Julia, firing up the package manager, and asking it to install the CUDA package. Once you do using CUDA and you do any functionality, for example, I'm calling the version info function here, which will give me some details about the setup. And then we will automatically download the CUDA toolkit for you in a way that matches exactly the driver you have installed. This is very user-friendly, and especially because it tends to be tricky to keep the exact correct version of the CUDA toolkit your driver requires installed at all times. Of course, it's also possible to not use it and just have CUDA.gl use your local CUDA installation, which might be useful when you're working, for example, on a cluster or on a non-network system. And you can do so by defining the Julia CUDA use binary builder equals false environment variable. All of this is also supported on all major platforms, namely Linux, Windows, and Mac OS, insofar that NVIDIA is still supporting the Mac OS platform, for now at least. So once you have CUDA.gl installed, you can start by using its array abstractions to program your GPU. For example, you can instantiate a QArray with an undefined set of values. Here I'm specifying the dimensions 2 by 2. You can copy that array or creating a similar array by calling the similar function. You can upload and download data by passing a CPU array to the QArray function or passing a QArray to the array function. So all of that must look familiar to you because we do our best to mimic the base array interface. Similar functions you might also expect there to be there, for example, is the ones function, the zeros function, a way to fill your arrays, or a way to generate random numbers. So all of that, again, we try to stick as close as possible with the base array interface. Other operations you might expect is to create a view such that you get a subarray that indexes a part of your array. You can also compute the sum of a GPU array. You can perform element-wise multiplications, take the adjoint, perform matrix multiplications, and so on and so forth. So again, all of that matches the base array interface. However, of course, each of these operations are implemented using very fast GPU kernels. And whenever possible, we actually use the NVIDIA libraries, which typically come with very fast precompiled kernels. For example, if you request CUDA.gl for some random numbers, we will probably end up using the current library. If you perform a matrix multiplication, if the types of the array allows for it, we will be using cuBLAS. Same applies to cuSolver and lots of the linear algebra functionality, cuFFT when you call functions from the abstracts FFT's functionality, cuDNN when you're working with functions from NNLib, and so on and so forth. The real power from these array types, however, comes from higher order array expressions. For example, here I'm instantiating two arrays, A and B, with some dummy data, and then I'm calling the higher order map function, which I give an anonymous function that's going to be element-wise adding 1 to every element to the array. And this is very powerful because we, as developers of CUDA.gl, have implemented this map function, but we allow it to be composed with arbitrary user code that you're writing in your application. Of course, there's a way of doing so a little more succinctly, and that's by doing this element-wise operation called a broadcast operation. The same applies to reduction. We have implemented the map reduce function, which you can pass an arbitrary map and reduce function, and this will be compiled together to a single high-performance kernel. Similar functions include the accumulate function, the find first function. All of this is a very powerful array language that often obviates the need for custom kernels. If you're well versed in using these array verbs, so to speak, you often won't have to implement your own kernels. This is also much easier because if you want to implement your own kernels, you have to know how the GPU works, how CUDA works, while in this case, you're using generic array expressions that can work on all kinds of array types. You can be writing code that executes on the CPU and port it over to the GPU by just changing the type of your inputs and reusing all of the generic array operations you've written down. And as an example of that, here's some code I picked from this course where a user has created a small machine learning model. There's a loss function, there's a model, there's a training loop that does proximal gradient descent. And as I mentioned before, how should we execute this on the GPU? Well, by just changing the type of the inputs and the weights to the curate type. And as a result, this entire training function will automatically execute on the GPU, and it even performs reasonably well. As you can see in the chart, at some point when the input is large enough, it will be faster than executing this pretty naive model, of course, on the CPU. And again, this is a very best case scenario because each of these functions that we're calling here have been implemented in the CUDA.gl package. That may not be the case. And if that happens, you might be running in this dreaded scalar operation issue. If you're executing a function here, for example, the norm function on a GPU array, and you get this warning that the implementation is performing scalar operation, that means that we're falling back to an implementation from the Julia base library, which performs an element-wise operation. So in this case, there's a while loop, and it's going to take element by element of the array and incrementally compute the norm. That's, of course, very bad because the GPU is a parallel accelerator. So if we're processing element by element, this is going to be horribly slow. And as we compare the performance of this norm function, if we execute it on a GPU array, it takes 9.7 milliseconds, whereas on the CPU, it takes only 3 microseconds. So this demonstrates that the performance of scalar operation is horribly bad. So that's why we have this functionality to disable scalar iteration. So if you want to write high performance GPU code, it's a good thing to disable scalar iteration, and then you'll get a hard error when you trigger this kind of functionality. You might be wondering, why do we even allow scalar iteration? Well, it's much easier to port code and not have it fail straight away if you can just temporarily fall back to this kind of slow operations, because sometimes you might just be doing it at the initialization of your data and not throughout, for example, the hot code part of your application. So you might wonder, why do we even need custom kernels then? So the one case would have been where if we're calling into some fallback functionality that does scalar iteration, you might have to write a custom kernel. Another might be that you want to fuse kernels. For example, if we have this array here I'm instantiating, and I want to compute the element-wise sum of an array and its inverse. It's a silly example, just to demonstrate that because we're doing two operations here. We're doing this broadcast addition and a reversal. This will not be fused together as you might expect from a broadcast expression. Instead, we'll be getting two separate kernels, which, as people tell you, is slow. So you should be wondering here, is that really slow? How do you actually measure that? But this is a good time to explain how do you do performance measurements on the GPU. And if you're familiar to Julia programming, you might be tempted to just stick an add time in front of your expression. However, that's not okay. That's very important. It's a common pitfall because many GPU operations execute asynchronously. So what you're measuring here is just the time to submit this operation, not to actually compute its values. That's why we have this add sync macro, which you can stick in front of your GPU expression, and that will synchronize the GPU. And as you can see how now the times are a fair bit larger. We also have, for convenience, a version of the time macro in the CUDA.gl package, which will do the synchronization for you and also give you some details on GPU allocations. And of course, it's always recommended to use the benchmark tools.gl package. If you combine that with the sync macro, you get a much better and much more robust timing of your GPU code. And if we compare that to the CPU reference, where we first transfer everything to the CPU before benchmarking and then perform the same operation on the CPU, we can already see that performing this operation, which is a silly operation nonetheless, but if we perform it on the GPU, we are about 40 times faster. However, plain timings like this often aren't sufficient, and in that case, you'll have to profile the code to see what's happening. And NVIDIA recommends the following workflow for that. So nowadays, NVIDIA has a suite of profiling applications, which is called Nsight, and they're composed of three applications: Nsight Systems, Nsight Compute, and Nsight Graphics. We won't be bothering with the graphics part of this, but the basic gist here is that you should always start with Nsight Systems to get a bird's eye overview of your applications. And once you know which kernels to optimize, you'll start using Nsight Compute for more details. So let me illustrate how to use these tools with Julia. So for the application profiling, again, which is always the first step you should do, you can launch Julia under the ansys profile command. If you then perform some operations, for example, the element-wise addition to the reverse I've been demonstrating, as soon as you exit Julia, the report will be written to some file you can then analyze. There's a better way though. If you, instead of Nsight profile, do ansys launch, you can do so interactively. And by marking the code you want to profile with the add profile macro, you get again the report file. However, you can then resume your work in your REPL. And this is extremely powerful because then on the one hand, you can just, for example, use revise to edit your code and profile it without having to restart Julia. And this is crucial because the GPU stack has some overhead in terms of how long it takes to load all of the packages and the compiler. So then on how to analyze this file, you can do so using the command line tool and sysstats, then you get some details. But it's much easier to just use the user interface. And then you can see this timeline. And you can see the two kernels I've been talking about. The first kernel that performs the reverse, and then the broadcast that does the element-wise addition. And the timeline is important because, for example, let me do something silly and call the identity function on a bunch of very small arrays on the GPU. We can see in blue that these kernels, they are very far apart. This is a so-called sparse timeline. And this is bad for performance because you won't be benefiting from the performance speed that the GPU can give you, because at this point we're bottlenecked by submitting work, which is a very small amount of work. It's a very simple function, the identity function, and we are doing some very small arrays. So if we arbitrarily increase the arithmetic intensity by, instead of using the identity function, calling the sign function, and doing so on an array that's much larger, you can see that the kernels take larger to finish, and as a result, you get a nicely packed timeline. This is much better, and that's also something to worry about when optimizing GPU code. Another example of a much more complicated timeline I've been working on today demonstrates that you can also enrich the timeline with information from the CPU. If you use the NVTX, the NVIDIA Tools Extensions library, which is also part of CUDA, so if you just install CUDA.gl, you can load this submodule. And it has this convenient range macro, which you can use to annotate code blocks on the CPU. And then you'll get to see your block you've annotated in the timeline view on the GPU, on the GPU's profile. And this is, again, also a very important tool to figure out where code you've been calling comes from and what the, again, bird's eye performance characteristics of your application are. Then the second tool I've been talking about is Nsight Compute, and that's a tool you can use to analyze kernels specifically. It works similarly. You can also use it to just profile a Julia session, or if you exit Julia, then you get some characteristics on the kernels that have been launched. And you can, again, also do so interactively, where if you launch it with mode launched, you regain control of your REPL. Instead of just using the command line tool, again, similarly, we can use the user interface by attaching it then to the session, and all of that is documented on the CUDA.gl homepage, so don't worry if you can't follow at this very specific point. I just want to mention that this is one of the important tools that you need to use if you want to profile kernels in detail. Anyway, back to our original session. So as I mentioned, we have these two kernels here, and we were wondering whether that's expensive or not. So let's try and write our own kernel that performs this operation, the element-wise addition to the reverse, in a single step. And a kernel looks like this. So we define a function. This function will be responsible for processing a single item, much like in CUDA C. We then compute the index of our current function, and for that index, we will be computing the destination element. So you might think that because we could do this reversal on the CPU, we can also do that reversal on the GPU. However, if you try to do so, this will fail. You'll get a compilation error mentioning something in the array backtrace. And in this case, this is an important example because it illustrates how programming Julia on the GPU doesn't give you access to Julia's C runtime library. And this makes it so that you cannot use certain pieces of functionality you might be used to using on the CPU. These include dynamic allocations that rely on the garbage collector, dynamic dispatch, input-output, or in this case, the CPU array type. And calling a reverse will allocate a CPU array type, and as a result, you cannot use so in a GPU kernel. Solution is simple. Instead of calling the reverse function, we just have to do the indexing from the end ourselves. We do here by using the end keyword. If we launch this on the GPU now again, using the add CUDA macro, we get yet another error. And this is to illustrate that even though we're working in a high-level language, Julia, the rules of CUDA still apply. And in this case, the rule is that you can only launch a certain number of threads within a single block. And we're launching length of a amount of threads here, which is 10 million, and that exceeds the limit of 1024 threads. So we still need to abide by CUDA's rules. And in this case, that means that we have to launch a number of blocks, and then we can compute our index of the current element by multiplying the dimension of the block with the index of the block and then adding the thread index. This is very similar to programming in CUDA C. So if we then launch this kernel, we can see that the performance is a fair bit higher compared to when we did the separate kernels naively using the array operations. So this might be another reason that you want to write your own kernel because of performance. An easier way of configuring how a kernel is executed before we hard-coded the amount of threads, but it's typically recommended to use the occupancy API, where in this case, we're going to compile our kernel, but we're not going to launch it by setting the launch keyword to false. And then you can inspect all kinds of properties of the kernel. And one property you can expect is querying the launch configuration API from the CUDA toolkit. And it'll tell you what the ideal amount of threads is you want to execute for this kernel. And then we compute how many blocks we need. And we launch the kernel with that configuration. And this is a nice example of us exposing a very low-level API, the occupancy API, but doing it in a much high-level way that facilitates using these APIs. And this is something we try with all kinds of other CUDA APIs. So we try to expose your functionality wherever you need it. For example, you can do the basic indexing you need to do in a kernel. You can launch kernels with corporate groups. You can use shared memory, and so on and so forth. So all these features that you're used to in CUDA C are available with CUDA.gl, but whenever possible, we try to make them slightly more higher level. For example, in the case of atomics, instead of having to call specific atomic add or atomic inc functions, you can just stick the add atomic macro from the CUDA.gl package in front of an array expression, and it will try to perform that atomically. However, of course, we only do so when performance is guaranteed. We will never raise the abstraction level of any of these operations if that comes at the cost of performance or flexibility. In terms of performance, you still have to do all of the typical optimizations you expect to do in CUDA C. You have to avoid thread divergence when you're writing kernels. You have to reduce and coalesce global accesses, for example, by loading into shared memory. And as I mentioned, you may have to make sure that your launch configuration is good, such that occupancy is improved. All of that is something you have to do when you're working with CUDA C, but there's also some optimization that uniquely apply to using CUDA with Julia. One of these is that if you allocate an array, because the array is garbage allocated, you might want to unsafe free it early on, which is a hint to the garbage collector that you won't be using this memory anymore and it's safe to reuse it early on. You also might want to avoid exception branches by annotating code with add inbounds or avoiding needless conversions, for example, from 64-bit to 32-bit integers. And generally, you also would want to use 32-bit integers because NVIDIA GPUs typically perform much better with them, whereas in Julia, much of our literals are by default 64 bits. When you're optimizing code like that, it's always useful to look at the generated code. We also have a bunch of tools for that. You probably know the add code LLVM macro from programming CPU code in Julia. Similarly, we have the add device code LLVM macro, which you can put in front of an add CUDA invocation or in front of an entire application even, and you'll get to see the generated device code. Similarly, we have add device code PTX, which will show you the generated PTX code. That's a level lower. And even a level below that, we have the add device code Seth, which will show you the shader assembly. Now, you might think that all these tools are advanced tools that are only there for expert programmers, but they're also very useful for debugging code when compilation goes wrong. For example, say we write this kernel that applies the sign function to every element of the array. If you want to launch this, we get a dreaded invalid IR error. And it's mentioning us that we're performing an unsupported dynamic function call. And as I mentioned before, dynamic function invocations are part of the Julia C runtime, so they're not supported. So this specific type of invalid IR error typically comes from badly inferred code. And a way to inspect badly inferred code is using the code warn type function. So again, for this kernel, we can use add device code warn type, and you'll see this any annotation, which indicates that type inference in Julia has not figured out the resulting return type of a certain function. And in this case, you might spot the issue. We have typed thread ID instead of the actual name of the function, thread IDX. And as a result, Julia wasn't able to infer the return type. And that's something that's not supported on the GPU. This is a simple case. However, sometimes it's a little more hidden. For example, if we have our issue in a child function, then we call this child function from the kernel function. We try to launch this, we get a different error. In this case, we get a kernel error mentioning that the kernel returns a value of type union. The empty union type is going to be returned from kernels and functions that unconditionally throw an error, and this is also not supported on the GPU. So as I mentioned, we can just use add device code warn type, but other than the fact that Julia inferred that this function returns the empty union, we don't immediately see where the issue may be. And that's where another tool comes in. It's called Cthulhu, and it's a tool that CUDA.gl integrates with when you specify interactive equals true to the device code warn time macro. And if you do so, you'll be able to interactively descend into the call stack. So in this case, the first thing we'll see is that the function is calling child, as we know, and Julia has inferred child to return the empty union. So we might want to descend into this child function to see what's up. And if we do so, we can see that it's actually the call to the CUDA cosine function that's being inferred as invalid because there is an unreachable at the bottom of that. And if we look some closer, we'd see that this function is being invoked with an argument type of complex F64, which the CUDA cosine function does not support. Sometimes it's a bit of trying to find the puzzle what's wrong, but at least with these tools, you'll be able to go to the bottom of the issue straight away. You might also be dealing with runtime issues. These are compile time issues, but sometimes we'll have runtime issues where, for example, there's some corruption happening. And for that, you can always use many of the tools NVIDIA has developed and ships as part of the CUDA toolkit. For example, this small kernel here, say it's going to compute the reverse because that's a running example in this webinar. Say we're trying to reverse in dynamic shared memory, but we forget to sync our threads when we are reading and writing from that shared memory, as a result introducing a data race. In order to spot these, you can run under the CUDA memcheck, which has a variety of tools. For example, if we enable the race check tool, we'll see that in our reverse kernel, there's a data race being reported. And CUDA memcheck has a variety of other tools. By default, it performs memory checking. It will also have synchronization checking and so on and so forth. So you can use all of these tools when you're doing some more advanced debugging of runtime failures. For some more advanced things users might want to do, we have written high-level wrappers that expose much of the CUDA APIs. For example, you can conveniently inspect and instantiate your device, work with context, events, streams, and so on. You will probably want to use those if you're working with more advanced applications. When we, of course, haven't had the time to create high-level wrappers for every piece of functionality in the CUDA APIs. And to cope with that, we also expose the entire C API. So for example, this function, the CUDA context-enabled peer access function, we don't have a high-level wrapper yet. Nonetheless, you can just use this function. You can even use it with these high-level context types or other types. They will get automatically converted to whatever the C API requires. And this gives you a very uncompromising access to the entire CUDA API, which is very important if you want to port code from, say, a CUDA C-based toolkit to Julia, because at least initially you can port it by just falling back on all of those C functions you had been using all along, and then gradually raise the abstraction level by using some of Julia's high-level wrappers we developed in CUDA.gl. So in summary, I think Julia is a great language for programming across all levels of GPU applications. On the one hand, you can work with arrays, which makes it easier to work with GPUs. You don't need to know how to write kernels. And it also makes it possible to write and reuse generic code, which is very important for programmer productivity. Of course, if necessary, it's always possible to still write your own kernels. And if you do so, you can get the same performance and flexibility as you would have gotten in CUDA C. And to facilitate all that, we have a bunch of tools, both tools from the compiler we've developed ourselves and integration with tools from NVIDIA that help both novices and expert GPU programmers doing so. And most of what I've explained here, sometimes a little fast, is also part of all of the documentation. You can find the documentation on the CUDA.gl repository. If you go to the GitHub site, you'll see a badge pointing to the documentation, which is linked here as well. We also have a more familiar landing page, which with some high-level information on the different backends that we have. And of course, if you have some issues or ideas, you can always drop by the Discourse GPU domain or the GPU channel on Slack. And with that, I'll have a look at the chat to see if there's any questions.
Tim, we do have two questions that just came in recently. One of them from Sheikh. It says, "Do you have a wrapper for CTX? Does that mean under the hood is it running C code?"
I'm not sure what is meant by wrapper for CTX. We do not run C code under the hood. So the entire stack is completely written in Julia. All of the kernels, all of the interfaces with the high-level wrappers were developed, all of the calls to the CUDA toolkit itself, all of that is written into Julia. There's no glue code that is written in C or C++.
Awesome. From Prasanna, does Julia natively support CUDA if CUDA toolkit and driver is supported, or did you have to modify, import anything on the Julia side?
Yes, it supports both the case where the CUDA toolkit and driver is set up already, in which case you can define a environment variable. It's called, maybe I'll go back to the slide. The environment variable is called Julia CUDA use binary builder. If you set that to false, then CUDA.gl will use the local CUDA toolkit. However, by default, the only thing you need is the CUDA NVIDIA driver, and CUDA.gl will automatically download CUDA for you. And that's the recommended way if possible, because then we ensure that the version we're using is a version that's supported by both CUDA.gl and your driver.
Awesome. From Carlo, could you briefly mention what is thread divergence?
Yes, thread divergence is a issue that arises with GPU kernels because the kernel you've written is a scalar kernel. So it's going to be processing element by element. However, in reality, the GPU's hardware will be processing multiple elements at the same time in lockstep. As a result, if you take a branch that for some threads in that unit of computation goes to the one side of the branch, and for some other elements go to the other side of the branch, the hardware will actually have to serialize computation and execute both branches. Essentially, you should be taking care that your branches all go in the same direction for every group of 32 threads. That's the concept of thread divergence, and it's a fairly common problem with GPU code. It's not isolated to Julia. It also exists in CUDA C.
Awesome. The next question is from Levi. What about multi-GPU and NCCL support?
Multi-GPU support is being worked on. So we currently do support actively switching from one device to another device and executing code on those devices. However, the array abstractions that I mentioned, the very high-level user-friendly ways to program a GPU, those haven't been made so that they benefit from multiple GPUs. So if you want to write an application and you do your own communication between GPUs and you want to manage yourself how computations and data is divided up, that'll work just fine. If you expect the application to automatically use whatever amount of GPUs you have by just writing generic code, that currently doesn't work, and that might not, it might still be ways off actually.
Okay, thank you. From Prasanna, and do you have plans to support ROCm?
ROCm is the toolkit that's being used by AMD GPU.jl, yes. And I just noticed that I forgot to answer a part of the previous question. What about nickel support? We have experimental wrappers for nickel. It's not part of CUDA.jl itself, though. However, if there's lots of interest for this, we can always polish these wrappers and make them part of the official CUDA.jl package.
Okay, so in looking at ROCm, you mentioned it's under AMD GPUs, and there are several follow-up questions on that with regards to AMD GPUs. Is it run on Metal or OpenCL or Mac OS?
Metal is an issue because we currently do not emit Metal directly. There is no LLVM backend for doing so. And if we want to emit Metal from SPIR-V, which is a IR format we have supported via the OneAPI package, and then we cannot use the so-called kernel mode. Long story short, Metal support is probably not going to happen anytime soon because of limitations in the tool chains that we do not develop.
And how about OpenCL on Mac OS?
OpenCL.jl is currently a package that can only be used to work with the OpenCL APIs. We currently do not support any native programming or native compilation from Julia code to OpenCL. As a result, the OpenCL.jl package can only be used in combination with OpenCL C code. Of course, for some users, that's not a problem. For others, they might expect to just be able to run Julia code. However, luckily, as I mentioned in my previous questions, we recently developed a SPIR-V backend, and we might be able to use that to make OpenCL.jl natively support Julia code in the future.
Awesome. So, from Antonio, could you please compare CUDA.jl and OpenCL.jl?
Yes, so I think I explained most of that in my previous answer. OpenCL.jl is currently just the API wrapper without the native GPU computation capabilities.
Awesome. And can we compile GPU code in an executable app like NVCC in Julia from Pravir?
Yes, native compilation capabilities into a binary is a work in progress, but actually does work. For that, I would recommend you to look into package compiler, which you can use to compile a Julia package or Julia project into a single executable. GPU support for that is currently experimental, but starting with Julia 1.6, which should be released in the coming weeks to months, it should be possible to also embed full-fledged GPU application in those package compiler generated binaries.
Very good. The last question we have here so far is Christoph, do you have to modify the internals of LLVM for all this to work? And then the follow-up question is, or just reuse the existing LLVM infra?
Thanks to much of Google's efforts a couple of years back, we get to just use LLVM. We don't actually have to change it much to support the GPU compilation capabilities I've demonstrated in this talk. We do maintain a forked version of LLVM, but that's mostly just containing some additional bug fixes and patches. The core functionality that I've explained here is also available in Clang for use with CUDA C there, but it's the same code generation capabilities.
Awesome. We can wait another minute here to see if any other questions come in. But it seems like we've gone through a lot of the questions. We've had a lot of thank yous on the chat, certainly for a great talk, Tim. Here we have another one from Sheikh. Can you compare the way PyTorch uses GPU and Flux uses GPUs? In case of PyTorch, there is a device method to send data to the GPU and later model should you be transferring to CPU for CPU use. And you might want to reread that in case I botched that one up.
Yeah, so that API, I'm not too familiar with the PyTorch GPU API, but the way you describe it here sounds very similar to how the GPU function works in Flux, which you use to transfer both your data and your model individually to the GPU. And then you'll have a model that lives on the GPU and data that lives on the GPU. If you afterwards want to transport that back, use the CPU function, which is also a function defined in Flux.
Very cool. Yes, a lot of people saying thank you. Another one from Levi is the Google LLVM flavor you mentioned, their MLIR project.
No, I wasn't clear there. I just mean that we're using the upstream LLVM base, but the GPU compilation functionality has been developed by Google a couple of years back as part of their GPU CC work. Currently, that's all part of just regular upstream LLVM. MLIR we're currently looking into, but we're not actively using because Julia itself targets LLVM IR, and retargeting that to MLIR is quite an effort.
Awesome. It looks like we've satiated the folks from the questions. Certainly appreciate your time, Tim. Everyone is saying thank you, so it doesn't look like we have any further questions, but if you have any questions, again, please use the discourse channel. We'll be more than happy to get back to you on that. If you have questions that are more commercially centric for your applications where you're targeting GPUs, feel free to write us at sales@juliacomputing.com, and we'd be more than happy to entertain your questions, get on the phone with you, sit down, have a talk, and find out how we can help all of you moving forward. Thank you so much. Thank you, Tim. Really appreciate your time, and have a great weekend, everyone.